Okay, that should you should be able to see the screen, the slide deck. Can everyone see that? Okay.
Yes, yes.
Okay, great. So today I'm going to be talking about some experience that we've had with supercritical CO2 systems, in particular supercritical CO2 applications for geosequestration, and in particular as well the compressor design for that. But for that, just a bit of an overview. This will be the agenda today. We'll talk about the problem. I'll provide like a short overview of the overall problem, and then talk about some of the three items that we were that we looked at for this particular situation. So the first would be essentially addressing the property estimation strategy for this, i.e. figuring out what sort of property package and what needed to be done with regards to the property package. Second is once you've got the property package defined, then we were taking a look at different types of concept select for the process, for the compression process. Yeah, so we found from this case that we couldn't use conventional configurations. We had to do some slight modifications on the compression system. And then after that, we did an anti-surge analysis for this system. So I'll talk about that in greater detail once we get to that section. It looked, this is pretty much the result. So with the anti-surge valve on its own, we found that the compressor went to surge for about 2.2 seconds and entered this particular region for about 2.2 seconds, came back out again. In this particular case, I think when we had discussions with the customer and the vendor, they felt that this was not feasible. So they still required the anti-surge valve to be implemented, as the fast stop valve to be implemented. In some cases, some vendors say that this is a reasonable amount of time. It's okay. So it really depends from vendor to vendor. But the important thing is to be able to have a look at to generate these curves so we have an idea of when we're in the feasible regions and when we start having excursions into the surge region. Now, I'd like to make a point, a very important point, that everything you're seeing over here, this curve and the behavior was done on HYSYS. And one needs to bear in mind that HYSYS is a thermodynamic-based tool. There's no fluid mechanics, and there's no mechanical effects. So everything that you're seeing, the way that the system responds, is based purely on thermodynamic characterization of the system. Therefore, it's important to use these kinds of tools as only part of your toolkit, part of your process engineering toolkit. Once you've gotten these results, you then have to reconcile it. You have to take a look at some of the mechanical aspects, some of the fluid mechanics aspects, put that all together, and then formulate your engineering decision. Yeah. So it's not enough just to take a look at these HYSYS or Unisim results, because they're purely thermodynamic bound simulators. Okay. So yeah, so in this case, we were able to protect to I guess guarantee a certain amount of protection level on the compressor and potentially avoid mechanical damage from surge. I mean, we've seen situations where compressors have gone into surge many times, and how it degrades the material and causes like ultimate like pretty severe failures. Okay. Okay, so that's just a bit of an overview of some of the work that we've done in carbon dioxide supercritical CO2 and geosequestration. So you can see that there's quite a bit that has to be done before you actually do the engineering work. You need to make sure that the properties are properly represented, yeah? Because that's essentially the foundation of all your computations. If the thermophysical properties are not properly calculated, then everything else is just going to fall through. Okay, so that's all that I have. I'd like to thank everyone for joining today. I'd like to thank MOGEC for very kindly inviting me for this. Yeah, so I'll open the floor to any questions if anyone has any questions.
Yeah, Engineer Rafil, thank you. There's one question in the chat box
Okay.
from Tia.
It's so long, the question.
Yeah. Let me see if I can open it.
Can you?
Hold on a sec. Question is from Chia Sinho. Okay. I'm Chia, the process engineer. Hey, Chia, from Acre. Above critical point at the discharge, HYSYS will indicate that the CO2 is having a vapor fraction 0, which means HYSYS will calculate the supercritical CO2 as liquid. As such, is it possible to simulate the fourth state compressor? Since the fluid is considered liquid, is it possible to simulate? Okay, so I think the question is as follows, and that's a very good question, because that's that's something that is that I've always encountered and something that I'd like to address. So let me. I don't know if you can hear the drilling.
No, Engineer Rafil, it's okay. We didn't hear any drilling.
Okay, so I only I can hear the drilling.
No worries. Okay.
Okay. So just one thing about using HYSYS, about using HYSYS and all these other tools, is as follows. And you have to be very, very careful. And this is one of the things that I always address, that I'm always addressing in the class. If I take a look at the phase envelope, the PT diagram. Okay, so let's say that is my critical point now. So in this case, I am subcooled. This case, I am superheated. Superheated gas, subcooled liquid. Here I have two phase. And over here, I am, this is my critical point. And here I am supercritical. Okay, so the interesting thing about these simulators is there will be a slot which says vapor fraction. And that number has to be between 0 and 1. Okay, now you've got the following states of matter. You've got solid, liquid, gas, supercritical, and plasma. Okay, so most of the time in oil and gas, for most process engineers, so if I see you, say for example, if you're from Acre or Worley or most of the oil and gas process engineers, most of the time you're going to be dealing with these phases lah. Yeah. So in HYSYS, we know that if something is liquid, the vapor fraction will be 1. Sorry, the vapor fraction will be 0. If it's a gas, it will be 1. If it's supercritical, these numbers actually become meaningless because it's neither a gas or a liquid. There's no separation. There's no energy pretty much in this region. And the convention of HYSYS is it depends. If you're somewhat over here, I can't remember the actual criteria. If you open up the manual, it should be able to tell you the criteria. If you're here, then it will assign a vapor fraction of 1. If you're more vapory, if you're more liquidy in this region, it'll assign a vapor fraction of 0. But these numbers are meaningless. Yeah, the numbers are meaningless. So it is not really a liquid. You can't really look at representing this this fluid as a liquid because it is not really a liquid. It's a completely different phase. So we treat it as a supercritical fluid and not really a liquid. If you put this through a separator, for example, depending on what is the vapor fraction, it will either go out the top or it will go out the bottom. Yeah. So is it? Yeah. So that's the case because it's a compressor, and as long as it's supercritical, then it is applicable to simulate it using a compressor. Yeah. So compressor is used every time you've got like a compressible fluid. And what is the compressor? Well, when do you use a compressor in HYSYS? One, obviously, when you have a gas. Two, if you're supercritical. And three, sometimes when you are near critical. So when you're within this, when you're near critical, can I get my color? When you're near critical, when you're somewhere around here, okay, where your density is starting to flip between liquid and vapor, is actually quite compressible. You know, it's quite compressible around this region. So while you're around here, also, it might be necessary for you to use a compressor object. Yeah. If you have pure liquid, if you're subcool liquid, if you're pure liquid, then you use a pump object. Yeah. So that's why we can still use a compressor in this case. Actually, in the simulation, as we start getting farther into about like a 600 bar, I still use the equipment that you buy is called a pump. So they're using these Nuovo Pignone pumps, but we are modeling them using the compressor object because the supercritical fluid is still compressible. Yeah. So I hope that that answers the question. Is that okay, Chia?
Yeah, can you give some thumbs up or reaction?
Or if you have some other questions, we can take this. We can take this offline as well. You know where to find us. Okay.
Yeah, she said, he said, okay, thanks.
Okay. So I have another question.
Yes, Yi.
From Yi. Just wondering if we were using machine learning or AI to tackle this problem, can AI machine do thermodynamic tuning of equation state? Okay, so let's take a look at what we mean by AI. Okay, so when you take a look at AI, it's a broad encompassing term. One of the things within AI is neural nets. Yeah, what are neural nets? Well, neural nets for someone my age, they are essentially a bunch of statistical functions that you tune, that you have to regress or you train. Yeah, training is essentially another word for regression, lah. So thermodynamic tuning is one of the. If I were to use this analogy, when you tune your thermodynamic packages, it's analogous to what you're doing when you train your neural net. You've essentially got a structure, and within that structure, some tuning parameters, and you do some regression. So if you talk about AI or machine learning, a lot of times that's essentially what you're doing. You're training or you're tuning. You're sending it. You're tuning it. So if you're there's a couple of things you could look at. If you're already using like a Peng Robinson or SRK framework, then inherently you're just tuning it. If you want to go completely AI and forget about that, well, one thing is maybe you can put like a neural net together, like a multi-layer or a multi-layer neural net, and you can have certain inputs, specify certain outputs. For example, input CO2 content, temperature, pressure, or something like that, vary that, and then predict all the other properties, meaning that there's no sort of mechanistic relationship between the inputs and the outputs. But if you're already using, I guess, like a property package, the inherent tuning of that property package would be analogous to, I guess, like a data analytic activity. Yeah. So that's one of the things that we do. There's the traditional tuning by regression, or in some cases, I've seen people just replace the property package just with a neural net. So when you replace your property package with a neural net, you don't have all of that fine representation. So let me just see what I mean by the representation. Oops. And I've lost it. 1 second. Here. So, so in this case, I've got like a mechanistic representation of all the various properties over here. And I've got like some form of, even though these are empirical, but there's still a bit of mechanistic information, for example, that I can still have a physical feel for, like V minus B. So that's the volume exclusion, because molecules have non-zero volume. So I can only squish a certain amount. They're going to resist. Second, these they're kind of like magnets, yeah, the attraction term. So that's what the attraction term is. So they might, when you bring them close to each other, they might stick. So these terms over here have some kind of like a physical a feel to them. So when I'm tuning, when I tune, say, for example, the Kij, it would just be a matter of regressing the parameters. So there isn't really much AI or machine learning that one would do for that. One thing that maybe the machine learning or the AI could do is identify good data sets for tuning. Because in order to tune, you need a lot of data sets. And one of the things you do is you might go and buy the data sets, either from GPSA data book or Decima, Dipper, TRC. And you have to sift through a lot of those details using thermodynamic consistency rules. So that's one thing I think you could probably use to help with the tuning. Use the machine learning to select the thermodynamically consistent data from all that mess of data. So even though you buy the data, it doesn't mean that the data is good. You still have to do thermodynamic consistency checks. Yeah. So that's one thing I think I've seen also someone using AI as part of the tuning to sort out all the bad data. Okay, I hope that answers your question. Okay. If you have any other issues, just give me a shout. We could also take this offline. Okay, so the next line over here
is Wu from Technic.
Wu.
3:58 p.m.
Okay, we can get different water saturation gas. That's correct, using different packages. Which one? That's a good question. ICO2 90% different EOS. Yeah, I think in general, I don't think HYSYS is going to give you like a good, a completely accurate representation of water saturation if you use it out of the box. You'd probably have to you would probably have to look at it as a separate computation, do a different hand calc or something if you really wanted to get some accuracy around there. From my experience, if you use Peng Robinson or the property packages out of the box, it might not, generally is not going to give you anything satisfactory. I think there are some, if I'm not mistaken, within HYSYS, I can't remember because I haven't looked at this for a while, but if you do a search, if you look at the manual, one of those property packages is supposed to be tuned for high water content, but that's high water content in natural gas and not CO2. So with regards to CO2, I'm not sure. What you'd probably have to do is to do a check. Maybe you might have to do a retuning, or you might just have to do a hand calc to compensate. So I'm not sure which one. I just know for sure that I don't think it's very reliable when you have high CO2. Yeah. Okay. The next question I see from
Minyi.
Minyi.
Yes.
From Wally. Hi.
Yes.
Okay. What EOS is proposed supercritical if Peng Robinson modified BIP adequate or good? So my question is, I already have in my toolkit Peng Robinson, and I've already done the tuning and everything, so I would use that because I feel comfortable with it. I have been looking at GERG 2008, I think. I can't remember which one. I think GERG package is kind of hard-coded. You can't tune it. It's supposed to be already tuned. I have not used it for high CO2. I've seen a couple of papers where it's compared against Peng Robinson. for certain density calculations. I personally, I've been asked this question many times. Unfortunately, I've never used it myself because I've already got like the Penn Robinson package that I've already tuned. So I'd be interested to see to see some more papers. I honestly speaking, I think I need to read a lot more of these new about these new packages that are coming up, because I'm still kind of used to the old 1970s, 1980s cubic equations of state. So you use, I guess, what you're confident with, and unless someone can show me that GERG is getting better, predicting better than my the error that I'm getting on my particular Penn Robinson with my tune parameters, then I'll probably still use that. Okay. Next question I see from Muhammad Rosdi Naim.
Yes.
We can adjust the dense factor to increase the phase envelope so it will be within the vapor phase. We can adjust the dense factor. I'm not sure. I'm afraid I don't quite understand what the dense factor is. Increase the phase envelope so it will be within the vapor phase. Oh, I think you're saying to adjust it so that the so that the dense phase. Not sure. Data. Yeah, I'm really sorry. I'm not sure what this is. Shimo, we can't activate mic for participants. Huh?
You want to unmute all of them?
Can I guess everyone just stop one by one lah. So maybe I can get like a better understanding, because I don't quite understand what this is.
Hold on,
Maybe
I'm trying to.
the dense factor to increase the phase envelope.
Allow my.
Well, I think whatever it is, you need to use the right equation to state in general. I'm not sure what this. I'm not sure what the dense factor is. Maybe we can take this. Maybe we can take this offline, or you can give me a shout.
Yeah, I mean, okay, I already, I mean, the attendees can unmute themselves. So
Okay.
yes.
So Rosdi, maybe you can tell me what you mean by this. Rosdi, can you? You good?
Yeah.
Good afternoon.
Yes.
Great.
Well, okay. Actually, my question is regarding this CO2. When we have this high CO2 content in the gas, you can see that normally for the third and fourth stage, normally after we compress, and then the discharge gas, when we cool it down to our, let's say, 40 or 35 degrees Celsius, it becomes liquid.
Yes.
Yeah. So okay. What normally so far we are practicing here, we just increase dense factor so that we increase the envelope of that the phase envelope, so that the vapor phase will be we remove that dense region.
So normally, for example, we'll be going something like this.
Yep.
Right. So that's the aftercooler. This part will be the this will be aftercooler.
I share the screen.
Correct. Lepas tu kita compress.
Yeah. Okay.
Right. So if let's say if I'm in the sometimes you might end up something like this as well in the two-phase region, something like that lah. Yeah.
Yeah. What happened? We get the liquid after discharge cooler.
Yep.
So you get the
Yep.
So and normally, what you wanted that still within the vapor region, so that we can go for the next stage, right?
So after you set it, you get the vapor and you go to the next stage, correct?
Yeah.
Yep.
The problem is, for example, after the third stage,
Yeah.
Become liquid. The whole gas become liquid.
Okay. So when something like that happens, what's happening is that's because you dah sampai the cryocondensate bar.
Yep.
Okay, you dah sampai the cryocondensate bar. So the solution for that's a very good question, because I used to encounter this a lot. Your simulation, kalau if it's the solution is actually very easy for this. So normally kalau dia dah liquid, it will come out the liquid nozzle, and it will not send to the next stage, right?
Mm-hmm.
Is that right?
Yep.
Yeah. So the solution for this is very simple. You just don't put in your separator. You just feed it directly from here. Kalau you dah tahu that this guy is going to go into the supercritical region, that means you need to do a computational check. Make sure that this guy is supercritical, and then you can just don't use a separator object. Just send it straight into there. You know what I'm saying?
Yeah, we can do that, but
yeah, because the separator is not really doing anything. If you're in the supercritical region, if you're already in this region, the separator is meaningless, because you don't have two phases, and you're doing a steady state computation. And your steady state computation, the separator is there just as a phase disengagement device. It's there to disengage the phases. There's actually zero holdup in a steady state separator. It's not doing anything other than separating the phases. But if you only have one phase, then it's useless. And if you know already that that phase is supercritical, you don't need to put the separator in. You can just put a note saying this is supercritical. I'm bypassing the separator. Or sometimes if the customer still wants to see a separator object over there, you can take this, just put it through a mixer, and then send it to the compressor. But you must be sure that this guy is supercritical.
Yeah, there's a problem then, because we also not sure that the EOS that we are using, really accurate. And then we also wondering that whether this compressor vendor do their own simulation and anticipate this kind of scenario, and agree to change that configuration to have to eliminate for this the separator.
No. Okay, when I'm talking about eliminating the separator is my simulation, this simulation model is approximation of reality. Just because I do not have a separator in my simulator does not mean I don't put a separator in the field.
Oh, okay.
Okay, that means in my simulation, see, all of these things they're just like mathematical libraries. So if I know that this guy is not being used, I just don't put it in. I don't need to put it in just because I need a picture of that in. But that does not mean that I don't have a separator in the field. Is that clear, Doc?
Yeah, it's clear to me. But in reality, how we model it accurately so that we can design it properly, rather than I know that there will be a lot of experimental data to be checked against the one that we have. Normally, I think quite a phenomenon now when we have high CO2 content in the gas. This kind of thing will be happen. I think quite typical
Correct,
now.
correct.
The problem.
So your question is this: how do I know that this phase envelope is correct?
Yes.
Right? How do I know this is correct? So that's why I did before this analysis. That's why we did this thermodynamic. That's why we did this study. We did the validation. So I had to go out and buy. I had to go out and buy data. I had to pay for this.
I see.
So after paying for that, then only I know that okay, this envelope ngam. This envelope is okay. If this envelope is okay, then that's fine. The simulator might throw a 0 or a 1 for the supercritical, but I don't care. I know that the property that it calculates is going to be correct because I'm checking for the density. 0 or 1 is an arbitrary definition by the simulator. So I can say that if benda ni memang dah if it is, sorry, I'm kind of like mixing my Malay and English. If if I'm sure that my system is indeed supercritical, in my simulation, I might decide not to put in a separator, but put in a note and saying that I am modeling this without a separator because it's supercritical. In reality, I would actually have a separator as a scrubber here.
Okay.
Yeah. I hope that answers your question.
Yeah. Thanks a lot for that. Yeah.
Okay. No worries. If there's anything, anything else, just give us a shout.
Sure. Thank you.
Okay.
We have another one from Shri, process engineer.
From Shri. Okay.
Yeah.
Shri. Can you explain how the BIP tuning is done? The BIPs are input in the HYSYS based on experimental data. Okay, that's a good question. In my case, it's very simple. I outsource it to my friends. That's how I do it. I used to do it myself, but what happens is there are some, if you're using, say, Aspen Plus or the any of these Aspen toolkits, there should be like a regression. There's a regression tool where you essentially specify the data that you have and your targets. It might either be like a density calculation or it might be a saturation point. Yeah. So I think if you're using HYSYS, it's not directly in the HYSYS package. I think it's somewhere else. I can't remember exactly where it is in HYSYS, but there's a specific regression tool that you need to use. And then you choose a property package that you want to regress, Peng Robinson, SRK or something. Then you have to get all your TXY data, TXY, PXY data, and then set particular objective functions. And then it will adjust the interaction parameters until those objective functions are satisfied. So the objective function might be like a saturation pressure or something. Yeah. So that it would be in specific environments. I think if you're in Acre, you should probably be having HYSYS or the HYSYS package. I think I can't remember exactly where that tool is. They have it in Aspen Plus as well. Actually, I'm more familiar with using it in Aspen Plus than I am with HYSYS, because in Aspen Plus, it's actually built into the Aspen Plus package itself. Yeah. So that's if you got any further questions, we can obviously take this offline. Yeah.
Right. Okay. Thank you for the question. Thank you, Engineer Rafil. But before we go, can we have a group photo?
I think I got a question from someone put up his.
No,
okay,
that one is Rusdi
okay.
now.
Okay.
Yeah, can I have like a group photo with everyone? Switch on your camera.
Oh, so actually, I forgot one more point.
Yes.
Kalau you pakai Unisim, in Unisim, so who is asking apa ni yang tadi who's asking me that question? You can't do this in HYSYS, but you can do this in Unisim if you're a Unisim user. Apa ni Rosdi? If you're a Unisim user, you can actually tell the stream to say that I'm a gas. Treat me like a gas. So that actually solves. Unisim has actually solved that problem in steady state. HYSYS, bila you when you're in the supercritical region, it'll either flip you back between 0 and 1. But Unisim, you can actually force it to say, treat me like a gas or treat me like a liquid. So Unisim has that phase forcing feature inside. HYSYS tak ada. I forgot about that. Okay, sorry. So that's I wanted to add that on in case someone in case there's some Unisim users.
Is it the one that Azrael posts, can set the
Azrael posts inside the chat box.
Okay. Understood. Okay. Dense phase, the DPT alter predicate liquid. Okay. I see. That's vapor. DPT can be smaller and greater than 2. Okay, and you'll be applied in the supercritical region. Okay. Should not be applied when not in the supercritical. Okay, this makes sense. Liquid phase boundaries. Okay. I've actually I have not utilized this, because normally what I do is I will do based on what I would typically do is I figure out if it is supercritical already, then I don't care. I just don't use the separators. for that. So I don't force it to be a liquid. I don't force it to be a vapor, because those numbers, those zeros or ones, are not particularly useful. So I see what this is now. I'll actually have a look at that. Thank you very much for pointing that out. I didn't realize that they had put this in. I think this is HYSYS, kan?
So yes, HYSYS.
Okay. Yeah, I've not utilized it. So no, the strategy that I use is generally to remove the separator if I know for sure that it's supercritical. This one is a similar kind of hackler. So it's like essentially to force the number to be 0 or 1. Maybe this might be similar to what they're doing in Unisim. Yeah, I think it should be good. One of the things that if you want to use this, if you want to use a dense phase tuning factor, the only thing that I can say is do the default calculation. Lepas tu check your thermophysical properties. Check the density, particularly like density lah. Yeah, check your density. Lepas tu try to change that number to make it change the phase and see if the density changes a lot. If the density changes a lot, then you should use it as with caution, because that means that it's actually changing some of the it's changing some of the flash calculations rather than just changing the 0 or 1 assignment. Yeah. So yeah, thank you very much for pointing that out. I've not used that particular factor before. I just tend to just ignore the 0 or 1 once I'm supercritical. Okay, I learned something new today. Thank you. I guess I owe these guys, whoever posted this to me, I owe you a teh tarik or something next time we see each other.
Hello, I'm Chia here.
Oh yeah,
Yes,
Chia.
Chia.
Okay.
Thanks for Mr. Rafil explanations. Now, I very agree with you saying that if we want to change these tuning factors, we have to be very careful, because especially for CO2, when it's in the supercritical region, the CO2 itself is like the property is like a liquid. At the density, you can see that it's like 800 something kilogram per meter cube. So you have to be very careful. If we change that tuning factors and the properties, especially the density, like become very much reduced to like a vapor, then it's not correct.
Yeah.
Not only the density, I think the viscosity and all those things also is very much like a liquid. So we have to be very careful on that.
Yeah.
The only thing is that Mr. Rafil, just now when you answered me about simulating those CO2 at a very high pressure above the supercritical, I did the try before that. Yes, it still can run under the using the compressor. The only thing is that HYSYS will come out with a message saying that you have liquid in your compressor, and that icon will turn yellow. So, sometimes we are a bit curious to say to think that is there anything wrong with any wrong data when this thing is like turn into yellow? Because no, that means
that's
it's
fine.
still it's just a warning. You mean just a warning message in terms of predicting those properties, all those things is still okay, as you say.
Correct, because the compressor is just purely a polytropic process. It's just going to follow the path of entropy. Yeah, it's an isentropic process, so it doesn't really matter. Now, even if you look in the manual, in the simulation manual, it used to tell the user, even if you are looking at the liquid phase, but the liquid phase is very close to the critical region, it tells you to use a compressor rather than a pump, because the fluid is compressible. If you use the pump object in HYSYS is only for incompressible fluids.
Okay.
HYSYS does not handle liquid very well, HYSYS cannot handle liquid. So there's no bulk modulus or anything attached to the liquid. So the liquid is essentially considered like a block of lead. You can't compress the liquid at all. So that's how the pump works. So you have to be careful when you use the pump. It's only for liquid, only for incompressible fluid.
Okay. Thank you.
Yeah. Okay.
All right. Thank you. No more. There's no more question. All right. Okay. We shall take some group photo.
Okay.
Can I have everyone switch on your camera? Engineer Rafil, can you close your slide for a while?
Oh, kejap.
Yeah.
Okay. So this is probably one of the more fun Fridays I've had, because normally no one wants to talk thermo on Fridays.
It's a good session today.
And I learned something new. I'm going to go and play with that critical tuning parameter as well. So I know I owe a couple of people some teh tarik for that.
Okay. I can just snap now. Okay. Okay. 1, 2, 3. Okay. Hold on. One more. Okay. 1, 2, 3. All right. Okay. Should I share any you want to say?
Yes, if I may, just 1 minute of comment or input. I always love hearing Rafil explaining about this process engineering stuff. He makes it sound so simple, but I wish today we have more people from the project management or business side of the business attending, because there's always this discussion on why process engineering team takes so long to come up with some recommendation on equipments and etc. I think now we understand why that is so, especially when you carry out EPC work and you have to be everything is cost and schedule sensitive. Rafil, we should take this discussion to the next level. Let's do it sometime next year, if you have time. Let's discuss that. And the other thing is, one thing very clear is, regardless of how good any engineering software out there is, experience still is very important. I'm sure everybody agrees with that now. And in closing, I think as engineering companies and as MOGEC members, we need to collaborate with each other. I think now, hopefully, I hope those who ask questions and those who have inquiries can contact Rafil directly, EAST101, either through CASMA, or if you have Rafil's contact, please do so, because it's very important that we work together to solve all these engineering problems so that we can continue to deliver successful projects in the coming future. And with that, Rafil, I thank you so much, and we hope we can have you again on MOGEC webinars in the near future.